Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about these instruments work from a narrowing in the pipe, since they measure the pressure before it and the pressure after it. That is, the differential pressure. These pressures can be measured thanks to the taps located immediately or at a short distance upstream and downstream of the instrument. To obtain the flow with differential pressure instruments, Bernoulli's theorem is applied, and this says that at points along a horizontal line of flow, the higher pressure regions have a lower fluid velocity, and the lower pressure regions have a higher fluid velocity. Yes, I also found it confusing at first. As you can see here, we have a pipe with a reduction, and we can see that in the upstream stop there is more pressure than in the downstream stop. And this is exactly what Bernoulli's principle says, since the fluid velocity after the reduction is greater than that before it. Here, PA, PC, and BA, BC are the absolute pressures and velocities in the area before the plate, where the fluid fills the entire duct and the contracted vein, while SA and SC are the corresponding sections, and P0 is the density of the fluid assuming it does not vary. Developing these formulas, we can determine that the volume flow and the weight flow are calculated in this way. Expressing the diameter of the orifice D in meters, the differential pressure H, the absolute pressures PA and PC in pascals, and the density P0 in kilograms per cubic meters. Then we can see that the volumetric flow rate can be expressed as a function of the differential pressure created by a depressive element, as QB is equal to K times the square root of H, where K is the empirical constant and H is the difference in heights of fluid pressure. It should be noted that all the previous formulas are approximate. However, in practice, correction factors are considered, and these take into account the distribution of unequal speeds, concentration of the fluid stream, roughness of the pipe, and the state of the fluid. For this, we add the discharge coefficient C to the previous equation. This coefficient is dimensionless and practically constant for any diameter of the same model, so it's normally provided by the manufacturer. The flow can also be calculated with the flow coefficient, which is a design factor that relates the difference in height or pressure between the inlet and outlet of a flow restriction, and that depends on the Reynolds number, which I will explain to you in the end of this video. The higher the flow coefficient, the less pressure drop. On the other hand, the mass flow would be calculated with this formula. Compressible fluids will vary their density throughout the vein section, as their pressure, temperature, and specific gravity change. To calculate the volume and mass flow of this type of fluid, we use the following formulas. As we can see, these expressions are similar to those of incompressible liquids, with the difference that an experimental expansion coefficient E is introduced to take into account the expansion that occurred during the acceleration of the flow. This doesn't depend on the Reynolds number and is a function of the pressure ratio of the specific heads for compressible fluids and of the element and pipe sections. In case we want to express the pressures in bar and the diameters in millimeters, we use these other formulas, which are also applicable for gases that follow the perfect gas law if the density is calculated from the density under normal conditions. Speaking of the perfect gas law, it is important to say that it is not so true when the operating pressures exceed 10 bars, and much less when the gases are close to critical conditions. Therefore, to calculate their flow rates, other formulas are needed. In the next video, I will explain this topic in more detail. Don't miss it! The Reynolds number is dimensionless and indicates the type of flow we have. Either laminar, when the Reynolds number is less than or equal to 2300, in transition, when it is between 2300 and 4000, and turbulent, when it's greater than 4000. And well, this will be all for today's video. Don't forget to give me a like and subscribe. I upload videos every Wednesday in Spanish and Friday in English. Adios! Apúrate para hacer café. Wait a minute. The higher the low coefficient, the higher